And we should be good. Okay, so this is CET236, and that's where we are in the semester. Today I want to start talking about superposition as the new topic, and maybe maximum power transfer if we get to it. I don't think I've officially mentioned the midterm, so it was on this slide for next week, but as you should be aware, I don't do midterm exams or final exams during class. I get you to do them individually with me on Discord as a part oral, part written exam. Okay, so please. Okay, yeah, Christian, other people have said that they can hear me. You can't hear me, so. Okay, so what you need to do with the midterm, and I'll talk about that on another slide shortly, is you need to book your slot. There's a deafen button. Which is that one? Oh, that's the headset one. Yeah. Okay. I don't think I used that one. There we go. Yeah, okay, that's what it does. Good to know. I don't think I've ever actually pressed that button. Okay, so that's where we are in the semester, and I still do want to talk a little bit about mesh and nodal analysis. We are going to be using them from now on in the class. But as far as actually introducing the topics, the only thing we have left to do is to go through the nodal analysis tutorial questions. We didn't have time last weekend to get to those. And as I said, I do want to introduce the superposition, the idea of superposition, and maybe maximum power transfer, but we'll see how we go. That's what the assessment is looking like. I think homework 4 for the mesh analysis was due last week, and I rejigged the nodal analysis so that the nodal analysis homework is not due until next weekend. The only thing due today is lab 4, and I think I gave an introduction to lab 4 last time. I apologise, I am behind in my grading for this course, so I apologise for that. I will try and get it up to speed by the end of the weekend, so that you're in a better position to know what your grades are. Yeah, I'm not too far behind, but I think there's at least one, maybe the lab that I haven't graded fully yet, so, or much at all. Some of them I've graded. So we'll see how that goes. So there's the midterm. The paper is available in Blackboard, and the paper is on this slide. So the idea is that I'm going to interview you about how to answer one question about charge, one question about resistivity, and one question about resistance versus temperature. And you need to talk me through how you solve each of those types of questions. As you can see, for the talk through, I'm not going to give you any numbers. I'm just going to give you X, Y, and Z maybe, or maybe T1 and T2 in the resistance versus temperature question. And you need to talk me through how you're going to solve each of those questions. Once we're done, that's the oral component. Once we're done with that, I will give you numbers for X, Y, and Z, and one question out of each topic area, so for a total of 3 questions, and I will get you to write up your answers and submit your answers to these questions into Blackboard once I've given you the numbers. Okay, but these are the questions you'll be asked, and as I said, the it's an interview style. I'm not going to usually with my exam questions, my oral exams, I will just read out the question as it's written on the paper and then expect you to answer. The more I have to speak, the less likely you are to get full marks. Right? If I have to prompt you for answers, then that means I think you don't know what you're expected to say, and that means I don't think you know the topic area well enough. I'm not saying you're going to fail, but most people, I think, out of all of the midterm or oral exams, including finals, that I've done over the last year and a bit, I think I've only failed 2 people out of about 100, just on the midterm. And those people didn't know, for example, Ohm's law, V equals IR. They just had no clue. So there was no way they were going to be able to answer any of these sorts of questions. Okay, you need to book. The booking link is on the link there. It's also, if you go to, let's go to the course in Blackboard and go to Tools for Remote Work and Bookings for Exams, and select CET236 Midterm, and that will show you the times I'm available. Right, I'm available. Next week is very busy for me, so I'm not available much until Saturday afternoon next week, and then there's those, and I think I made it up until April 3rd, just in case, but try and get everything done by April 1st if you can. When you select a booking and put your details in, that will get on my calendar, and nobody else will be able to get that time slot. The only time slots that I'm available are already up there when you go to that link, so please only use those links. I actually noticed somebody came in since I did this slide this morning, so I think now 5 people have booked, sorry, 6 people have booked their midterms, and that means 19 of you still need to make a booking. That's okay. I like I said, I hadn't officially told you about this, so please take this as your official notification that you need to book your midterm, and go book it. If anybody has complete problems in booking that any of the times, please let me know as early as possible. And April 3rd is not as early as possible. In fact, April is not early. So over the next week or so, please check your availability and get on the calendar. Jacob, that is the exam paper. What is on the screen now is the exam paper. So I want you to know the topics of this course. And one piece of pushback I get from students when I make the exam papers secret before the exam is they get surprised by something in the exam, and that I don't know, detracts from their grade, right? So I want to give you the best chance ever to show me that you know the topic. And I'm explicitly saying what that topic is by giving you the exam paper. I'm actually very, very tempted. I was talking to somebody during the week who he's ex-military guy, and he did some study after the military, and he went to one class, and the professor during the first lecture of the class wrote the exam paper on the board, the final exam paper. There was only one piece of assessment for the whole course, and it was tell me what you learnt during this course. That was it. And I'm really, really tempted to ask a similar question. I'm not going to. I'm going to ask more of a traditional question, but I'm very, very tempted to do something like that, because people learn different things, and sometimes it's interesting to have people play that back. Sorry, that's a bit of a long-winded answer. I hope that answers the question, Jacob. Okay. Yeah. So if you go to into Blackboard and go to Assessment and scroll down to Midterm, you will see the paper there already, and the front page has got some rules and some information for you, and then the paper is just what's on that slide. You're welcome, Jacob. I just redid. I just reorganized it so it fits better on a slide rather than on a exam paper type thing. Okay. So today's session, as I said, I think we should start off with a tutorial on nodal analysis. And then I might talk about some new material on superposition. And then I don't know whether it's homework 4, it should be homework 5 questions, I think. Because I think homework 4 is gone. So let's just make that homework 5, because I think homework 5 is the nodal analysis stuff. And then if we have time, I'll get to maximum power transfer, but we may not have time today. Depends on how we go. Sound like a plan? Okay, so let's have a look at tutorial 2. Right, so tutorial 2 is, we've done the first 4 questions. So Bishal, there's two components. I think if you read through the sorry, I just go back to that. So if you read through the front piece of the exam paper, you will see, if I could make it a bit bigger so you can read it. Right, that last item there at the bottom. After the oral component, you'll be asked to solve questions numerically and upload your analysis into Blackboard. Okay, so the first part of the exam is completely oral, and then I will give you some numbers for X, Y, and Z, or T1 and T2 in the paper, and then I want you to solve those numerically. Right. If you have a look at the midterm, let's just click onto it. Right, there is a rubric, and you can see that the oral components of each question are weighted at 25% each, and then the numerical version of the question is labelled at only 25% total for all three questions. Okay, and that way I can give you again, another thing that always happens in this course, particularly in exams, is students make numerical errors, and I want to everybody make you've seen me make numerical errors, sign errors, right? And while accuracy is important, I value understanding over accuracy. So I've weighted the oral component understanding pieces more than getting the numbers right. If you get the numbers right, you get a better grade, right? So I'm not completely saying don't get the numbers right, but the weighting is skewed towards understanding. Right, so in the oral, on the exam paper, right, there's three topic areas, and I'm going to ask you one question from each topic area, and I will choose the question, right? So I could ask Bishul questions 3, 6, and 10, and then I might ask Jacob questions 2, 5, and 8. Okay, depending on the my whim, really. Does that answer the question, Bishul? The actual midterm is the thing that is in Blackboard, right? And it's the thing that is partially on the slide that I had up in OneNote or on the screen before, right? It's not there now, but it's in today's notes, right? That's the same. That's just a screenshot of the PDF that I had up on Blackboard. Okay, any more questions about the midterm, since it seems to be a hot topic? I'm happy to answer any questions. Okay, so let's move on. And as I said, nodal analysis, and I think that, again, there are 4 questions. let's just quickly review what we've got to do with nodal analysis first. And I'm just going to go through the steps, right? Because, where'd it go? There we go. Right, so identify the nodes. Remember, a node is an area of constant voltage. Express the element currents as functions of the node voltages and the resistances, obviously. Apply Kirchhoff's current law at each of the nodes except for the reference node. Reference node, we already know the voltage is 0 by definition. And then distribute and group like terms and solve the system. And then I probably should add a sixth, because I remember I made the mistake the other day, right, is answer the question. Because sometimes just solving for the voltages is not enough, right? Sometimes there's a final thing. And in web work it's nice because you clearly don't get full marks until you've answered all the questions, but or all aspects of the question. But in the written components or in the tutorials, you've got to be careful, right? Because you don't get that prompt. Everybody okay with what we've got to do with nodal analysis? Okay, so I'm going to set up breakout rooms, and as usual, the people in the room at the top will take on question 5, and then the next group will take on question 6, and then the next group will take on 7, and then the group at the bottom of the view will take on question 8. So let me just see if I can remember how to do that. Oh, there are 5. I got that wrong. Let me so this is I got the wrong number, so if you can do, this is the group at the bottom, if you can attempt question 8, that would be good. So I got the group the number of groups wrong, so but if you can do question 7, that would be good. I got the number of groups wrong, but if you can do question 6, that would be good. I got the number of groups wrong, but if you can do question 5, that would be good. I got the number of groups wrong, but if you can do question 5, that would be good. I'm getting the group above you to do question 5 as well, so the with Drew, Jacob and Jonathan, if you want to join them maybe, or if you want to do it separately here, that's okay too. Okay, any thoughts on question 8? Question 8 is one of the more complicated ones, right?
I'm having trouble getting the thing to load. Just load for me finally.
Oh, really?
I was just getting everything queued up.
Yeah, it's a bit like that. Yeah, this one, it sort of starts out a little bit more easily because the nodes are already defined for you, right? And remember, with nodal analysis, the things you've got to look out for are voltage sources connected between two non-reference nodes. But I don't think that's a problem with this question. Or question 7 for that matter. So you do have two freebies though, right? Remember, if there's a voltage source connected between the reference and a node voltage, that means you immediately know what the node voltage is. Just be aware that one of these two voltage sources is upside down, so the voltage that it is labelled at will be negated when it's connected upside down between the reference 0 volts and the node. Okay, I'm going to move on to the next group. Hi, any thoughts on how question 7 might go? Right, remember the tricky bits with nodal analysis is when there is a voltage source connected between two non-reference nodes. And thankfully in this particular example there are none of those, so we don't have to do a supernode approach. The slightly tricky thing here is that one of the voltage sources is upside down. So when a voltage source is upside down, so that the positive terminal is connected to the reference, that means the other side goes down that number of volts for that node. Also remember that when a voltage source is connected directly between the reference node and another node, then that's a freebie. You know immediately what that voltage, what that node voltage is. And in this case, we've got two node voltages where we can effectively write down the node voltage directly, or the way WebWork puts that, we have a KVL equation rather than a KCL equation for that node. Okay. Okay, I'm going to visit the next group up. Okay, so this one is a relatively simple circuit, but there is a slightly tricky thing about it. Well, one of them is it's got a current source and a voltage source. The other tricky thing about the voltage source is that it's connected upside down, if you like. The positive terminal of the voltage source is connected to the ground, or the reference, the 0 reference point. So that means the node voltage on the other side, even though it's a freebie, it'll be the negative of the labeled voltage. Can everybody see that? Yeah?
Yeah.
Okay. So this is anytime you see a voltage source connected between the reference and another node, that's a freebie. It's only when there's a voltage source connected between two non-reference nodes that then we have to do the supernode workaround and replace two KCL equations with a KVL and a KCL. Okay, I'm going to move on to the other group. Okay, how are we going with this one? Has everybody figured out how to get it started?
I'm just doing the matrix right now.
Okay,
Open MATLAB.
very good. Ooh,
Definitely need more practice for nodal analysis.
well, that's why we're doing it, right? And there's a, I'll go through the nodal analysis homework once we've gone through the solutions for these, so that's partly why I put off the due date. I had originally scheduled the due date for nodal analysis to be today, but that's a little too soon. So I wanted to give you at least a week's grace after the tutorial before making the homework due. Okay, I'm going to keep going doing the rounds of the groups, and probably about another 5 minutes or so. Right, it's about 9:33, so maybe 9:38 or so. I'll call everybody back.
Okay, thanks.
You're welcome. Okay, so how's this group going? Any luck on getting the
Still working on it.
still working, but you've made progress, yes?
Yes.
Very good. Okay, I said to the other group, I'll call people back in about well, now 4 minutes, so 9:38 by my clock, and then we can go through solutions.
Okay.
Okay. Okay, how is this group going? You going okay? Deathly silence. So I'm going to call everybody back in about 4 minutes. So if you're working on the assignment, on the question, please continue, and I'll get somebody from this group. In fact, I'm just going to take a screenshot of all the groups so I know who was in which, and then I'll call people to answer. Okay, I'm going to call everybody back in about 3 minutes. So if you have a solution or are getting close to a solution, I'll kill all the breakout groups in about, like I said, 3 minutes.
I'll probably be done in 3 minutes, so that's fine.
Okay,
I
good.
think.
Okay. What did I want to do? Okay, I'll call everybody back shortly. I always just have to remember what the callback function is, but it's callback. Okay. Okay, it's about enough, so let's call everybody back. No, that didn't work. Capital B. Okay, so we're back. I hope everybody had enough time to get a solution or get close to a solution. And actually I forgot I need to fire up my copy of MATLAB. So let me do that before we talk. Okay, so I took a screenshot of the people who were in each group, so rather than doing the bingo that's interesting. Sorry, my MATLAB usually puts up its splash screen, and I normally expect it to be up there on this screen, but I've added another screen, and it's decided to go on my my monitor screen, the one that I'm looking at the video that's going out. Okay, and it popped up where I thought it would, but the splash screen was on the other monitor, so that's okay. Okay, so first group, who wants to have a go at talking me through how to solve question 5 using nodal analysis?
I thought I was doing right, but I think I got too high voltages. But I can talk you through what I did.
So
I got there.
So just to try and put your mind at ease a little bit, notice this is half an amp, and notice this is 4.7, so 4700, right? And you've got half an amp going through 4700, right? V equals IR, so the V for that is going to be half of 4700, which is 2350 volts, right? So the voltage is going to be pretty big.
Okay.
Okay, so we'll see. Yeah, I mean, I'm not saying you're correct, but I like that you're a little hesitant because of this high voltages, but in this particular case, it might be okay, right? Because there is, at least across R1, there is a high voltage. Okay, so you want to talk us through? Yeah.
Yeah. I did, the 3 nodes at the top, A, B, and C from left to right.
Mm-hmm.
And then my directions, I have them all pointing towards B.
Okay, so we go that way, and that way, and that way. Yeah.
Yep. And then starting at, I did VCL for, or KCL rather, for A. And that's negative of VA minus VB over 4,700.
Mm-hmm.
Equals, I did equals 0.5 amps. I don't know if that's right.
Okay, so I usually do it so there's an equals 0 on the other side, right, for KCL, and any current flowing into the node is a positive and any current flowing out of the node is a negative, right? So I would probably write that down like that, which would change the sign of what you have on the 0.5, right? Because the...
Oh, okay, gotcha.
Okay. Because my usual way of saying Kirchhoff's current law is that the sum of the voltages flowing into the node. So I try and keep to that definition. So if the current is flowing out of the node, like the IR1 is, the current through R1, then I negate that, and then I sum. The biggest issue with both mesh analysis and nodal analysis is usually getting the signs right. So I try and even for me, and I think I made a sign mistake last week, right? So it's worthwhile trying to be reasonably regimented about the approach. Okay, so keep going. Sorry about that. Yep.
No, I understand. So KCL for B then is we have VA minus VB over 4,700.
Mm-hmm.
Plus negative VB over 1,200. And then plus VC minus VB over 18,000.
Yeah, I think that's right. I should have moved the numbers for R1 and R3 up a bit so you can read them a bit better. Okay, and then that's equal.
That equals 0.
Yep.
And then finally for C, I just did kind of a KVL, and then VC equals negative 8 volts.
Right, and this is the tricky bit because the positive side of this voltage source is connected to V equals 0, right? So this is a drop in voltage getting from the reference 0 to C. So you've got to negate the voltage. So, but you're right. VC equals minus 8 volts.
And then from there, I just built the matrix.
Okay.
Solved in MATLAB.
Can you read out what your matrix was? The RF matrix.
Yep. Yeah. So going from left to right, first row is negative 1 over 4,700. And then positive 1 over 4,700. 0. And then negative 1/2.
Okay.
And then next row is 1 over 4,700. And then the next one is negative 233 over 211,500.
211,500. Okay.
And then the next one is 1 over 18,000.
Mm-hmm.
And 0.
Okay.
And then finally, the last row is 0, 0, negative 8, 0.
Okay, I would have written that a little differently, but let's see what answers you get. So what do you get? VA, VB?
For my VA, I have 2,913 volts.
Mm-hmm.
VB 563, and I'm just rounding to whole numbers. And VC, I have 0 volts.
Okay, so that's the problem with the way you've written it out, right? I would remember this is the VA coefficient, this is the VB coefficient, this is the VC coefficient, and this is the constant term on the right hand side. So I would have written this down as 1, 8, right? Because, or sorry, 1 minus 8, because there's a 1 in front of the VC here, and the constant term is a minus 8. So I would, I think it's the numbers are slightly different. They don't look too bad, but let me, because we already, right, we already got that VC equals minus 8. So that's contradicting.
I was kind of confused because I did that at first, and then when I looked at the units in, the K column, and I found that, one was amps and then one was volts. That's where I was confused. Like, why would, you know what I mean?
Right, and yeah, I can see the confusion, and that is correct. But the issue is these two here are KCL equations, so they're going to be in amps, and this is a KVL equation, so it's going to be in volts.
Okay.
Okay, but it's okay to do that once you get into the matrix, provided each equation is correctly unitized, if that's a word, right? If the units in each equation are correct, then I think it's okay. Once it gets into the matrix, you are likely to have different equations with different units in just about any linear system that you're going to analyze, whether it's electrical like this one or physical, right? In physical systems, you often get equations involving acceleration, equations involving velocity, and equations involving displacement. And each of those has different units, right? I'll go with the metric version: meters, meters per second, and meters per second squared. Sometimes they even have jerk as a part of the equation, right? Meters per second cubed, the derivative of acceleration with respect to time. But yes, you're right in being hesitant, but it's okay in this instance. Okay. And so
Yeah, I have better numbers now that I've changed it. Actually.
Oh, you changed it?
Better.
Okay. So what did you get?
So I got for VA, it's exactly 2,912. VB is 562.
Okay.
And then VC is -8, and that makes more sense, I think, right?
Yeah, that makes much more sense. So I was actually surprised at doing a 3x3 system. Normally, when I get a freebie like this, I try and take full advantage of it, right? And I just put -8 in here, and that way, oops, I hate it when it does that. I'm going to have to stop OneNote and restart it again. But when that way, instead of having 3 equations in 3 unknowns, I end up only having 2 equations in 2 unknowns. And so instead of being a 3x4 RF matrix, it's a 2x3 RF matrix. Because I already know the answer for VC Right, I already know the answer for ooh, it got rid of all of, don't you hate that? So you got 2912, 562 and -8 when you did that substitution. Okay, but what I was expecting, and it did it again. Sorry about this. When it starts leaving trails, I have to kill it and bring it back, and I don't know why it left trails so soon. And that way you can just end up having two equations, right? So in this case, it would be minus 1 on 4700, 1 on 4700, minus 0.5, and then 1 on 4700, minus 233 on 21500, and then here it'd end up being, BC is -8, so it'd end up being 8 on 18,000. Okay, because VC was -8, and that should give you exactly the same answers as the way you did it. There's nothing wrong with the way you did it. It's provided you get that last line correct. But I try to make things as simple as possible for me, so I would make full use of the freebie VC equals -8. Okay, thank you very much. Okay, so let me just see who was doing the second one. We had Christian, Hunter, Leonardo, and Matt. So does anyone of those people want to walk me through your solution to question 6? Hunter, do you want to give it a go?
Yeah, sure. I'd set the nodes up like in problem 5 where it's ABC and the top ones.
Mm-hmm. Yeah, always label them and the polarities of the voltage and the directions of the current. It just makes life so much easier, particularly if I have to interpret it afterwards. Okay, keep going. Yep.
I also did same thing as the last one where all the currents were towards node B.
Okay. Yep.
I wrote down VC was -8 volts,
Right.
since it's right next to the source.
Right.
And then I had to rework my equations after you said you like them set up equal to 0. So the I had for VA, I had 2/3 minus VA minus VB divided by 6 equals 0.
Okay, and the only reason I say that is to get the signs right. Okay, if you know that something flowing into the node is positive. The other way to do it would be to say that in equals out, right? So everything's positive, but if it's going into the node, you put it on the left-hand side, and if it's flowing out of the node, you put it on the right-hand side. Okay, that's another way to do it, but I tend to make it my personal preference is to talk about it as the sum of all the currents flowing into the node, and that means everything's on one side. Okay, but if you want to think about it as ins versus outs, or ins equals outs, that is also a valid approach. Okay, sorry about that, bit of a sidetrack. Node B?
This one I got so VC minus VB divided by 12
Mm-hmm.
plus VA minus VB divided by 6 and then minus VB divided by 12
Mm-hmm.
equals 0.
Yep.
And then my calculator, I can actually put the equations right into it and it'll spit out the answers.
Aha! That's it. That's cheating.
So I actually didn't.
That's okay. So what answers did you get? We'll try and I'll try and do the answers. So we already got VC. So what's VA? What answers did you get for VA and VB?
VA I got 4 volts and VB I actually got 0 volts, which didn't feel right, but I can send you my
VB is 0 volts. Okay, we can try that. So so let's try and figure out what the RF equation or the RF matrix is, right? So I'm gonna, like I said, I'm going to do my not cheating, but I'm going to do my shortcut and only do a 2x3 RF matrix by knowing that VC is already minus 8 volts, which we knew from up here. Okay, so in that case I have, let me go back to green, I have a minus 1/6 VA, I have a plus 1/6 VB, and then with the 2/3 on the other side I have a minus 2/3, and then I have a 1/6 VA. I'm going to make sure I get everything right. This is the VA column, this is the VB column, and this is the constant column. And then my VB is a little bit more complicated. I have a minus 1/12, I have a minus 1/6, and I have a minus 1/12. So that's minus 2/12, which is minus 1/6, which also 2 minus 1/6, so that's minus 1/3, I think, VB. And then I have minus 8 on 12 on this side, bringing it over to this side, it gives me plus 8 on 12, or plus 2/3. Okay, and let's see what that tells us in MATLAB, if I can figure out where MATLAB got to. There's MATLAB. So this is Q6, and I get minus 1/6, 1/6, minus 2/3, and 1/6, minus 1/3, oops, 1/3, and 2/3. Let's just see what that looks like. That looks pretty good. And then RFQ6 should tell me what VA and VB is. And look at that, 4 volts and 0 volts. So let's see why that is. Right, we know that this is 2/3 of an amp. So we know the voltage drop across here is going to be 6 by 2/3, right? Which is what, 4 volts? That sort of makes sense, 4 volts. And we know that this is minus 8 volts. So this is VR1 going by the passive sign convention, right, is that way given our direction of current. So that means that effectively there's no current flowing through R2, right? If VB is 0, then there's no current flowing through R2. So I think that makes sense. Well, let's just keep it going, right? So we've got a minus voltage on this side, and if our VB equals 0 is correct, that means the current flow this way is going to be, remember, I equals V on R. So our I equals minus 8 on 12, which is minus 2/3. Okay, so we know we've got 2/3 of an amp flowing in, and this is saying that actually R3 is going the other way because it's negative, and so we've got 2/3 minus, we've got 2/3 coming out of the node through R3, and that sort of makes sense. That's consistent with this equaling 0, right? Because we've got 2/3 coming in, we've got 2/3 coming out, and there's no contribution of current into node B from R2. Okay, so you're right. Seeing VB as 0 is a little concerning, but it all seems to be consistent. KCL still applies. If we did KVL, that would still apply. Okay. So thank you for that. So
real quick,
yeah.
for the bottom half of the matrix, how did you get 2/3? Or where did that come from?
Okay, so I was just looking at. Let me grab a different color. I was just looking at the constant piece, and the constant piece is minus 8 on 12. And then if I bring that over this side, it's going to be minus 8 on 12, which is minus 2/3.
All right.
Oh, sorry. Sorry, with plus. Sorry, if I bring it over this side, it's going to be. You're going to change the sign, so it's going to be plus 2/3.
Yeah.
Okay. And
thank you.
You're welcome. And for some reason, it's gone again, so I'm going to. Sometimes I can go for several lessons, and that doesn't happen. And then other times, like now, it's happening every page, just about. I'm not quite sure what the difference is. Okay, so question 7, and I've forgotten who was in question 7. Let me just see if I can drag that down. So we have Alex, Bishop, David and Ryan. Can one of you talk me through solving it? The first part of this question is already done, right? We've already identified the let me just move that up a bit. So we've already identified the nodes. So somebody want to talk me through it? Ryan, how about you? Okay, how about Bishop? Oh, Bishop said he might have to drop off. Looks like he's gone. Okay, David Dubac, any thoughts?
I didn't really get anywhere near solving it because I got the signs wrong on it, like right out of the get-go.
Okay, so
None of the numbering really made any sense.
okay, so that's all right. So do you want to? So I think there are 2 freebies. Do you want to tell me what the 2 freebies are in this one first, and then I'll continue.
Are you talking about A and D?
Yeah, A and D.
Because they're connected. Yeah. So you're getting A is 10 volts and D I believe is negative 10 volts.
Okay.
So you're getting on the opposite side of the power supply, right?
Right. So the thing though is that this big line is the positive side, and the small line is the negative side, right?
Oh, okay. Yeah. So it's the other way around then.
So
My bad.
that's
That's
okay.
what I mean by with the signs. There were a few spots there.
And the biggest problem with me and all students, the usual numerical issue is the signs, and that's why I've been I push the passive sign convention early. That's why I push Kirchhoff's current law as everything flowing into the node. It doesn't necessarily mean you're going to get it right, but if you're aware that that's a potential error and a likely error, then maybe you'll self-correct. Okay, so you're right. So that's now minus 10 volts, and VD is plus 10 volts. Okay, so that's really good, because that means we've got, instead of having 4 equations in 4 unknowns, we now have 2 equations in 2 unknowns, because 2 of the 4 original unknowns, the node voltages, we know directly. Okay, so that's a good thing. So now I'm going to draw all my element currents, right? And as I said, I actually like this setup, because for node B I can draw all the currents flowing in, and for node C I can draw a... Spencer, is there something? Are you okay, or can you go on mute?
Oh, I'm sorry, I didn't realize I was unmuted.
Yeah, go for it. Okay, so then KCL at B, right? We have IR1, which is VA minus VB on 3, and then it's going to be effectively 0 plus 0 minus VB, which ends up just being minus VB on 4, and then plus VC minus VB on 4 equals 0, and then KCL for C is going to be minus VC, and be careful, minus VB on 4, minus 0.2, which is 200 milliamps, and then minus VC minus VD on 5 equals 0. Okay, that looks pretty good. So now we can make use of what we know, right? So that's going to be minus 10 for VA, and VD is going to be 10. Okay, so now the only unknowns we have in these 2 equations are VB and VC. So let's see if we can write out the RF matrix for it. So for VB, we have minus a third. And I'm just going to write it out. Longhand, minus a quarter. And minus a quarter. And for VC, we just have plus a quarter. And there's minus 10 on 3 on this side, which becomes just 10 on 3 on this side. So the constant term is 10 on 3. No other constants. And then VB is plus a quarter, minus a quarter, right? Minus a quarter. And then VC is, again I'll write it out, minus a quarter, minus a fifth. And then the constant term, that's minus 2 plus 2 minus 2 plus 0.2, right? So that's, I think that's 1.8. Do you see that? That's so it's going to be, no, did I get that wrong? I got that wrong, I think. So that's minus 10 on 2 negated. So that's 2, bringing it over this side is minus 2, and then plus 0.2. So that's going to be a minus 1.8. Okay, and I think that's our RF equation. Let me see if I can plug that into MATLAB. So this is question 7, and I'll just type it in directly. Okay, and then RF Q7, we get minus 3.36 and 2.13. Let me just make room over there. So that means we get let's get drawing back. We get VB equals minus 3.36 volts and VC equals 2.133 volts. Let's just have a look at what that, so VB is minus 3.36 volts and 2.133. And that sort of makes sense, right? Because over here we've got a minus 10 volts, and over here we've got a plus 10 volts, and those two are gradually increasing from minus 10 volts up to plus 10 volts. So I think that makes sense.
Professor?
Yep.
In KCLC, you have the -2 plus 0.2. Where did the -2 come from again?
So I decided to not, or to know that VD equals 10 volts, right? So I substituted directly for VD because we know it already. So I get a 10 on 5, or a, yeah, so it's minus, so it's plus 10 on 5 on this side. So I get a 2 as it ends up being minus VC on 5 plus 2. This term ends up being like that. So I then take the 2 over this side to get a minus 2, and the 0.2 comes from here. So I get a minus 0.2 coming to this side.
Okay, thanks
Okay.
for clarifying.
Yep, no worry. You're very welcome. Okay. So let me just bring that here so I can get back to it. And okay, any other questions about question 7? Okay, I'll
What is V0? Because that's what it's asked to solve for.
I did it again. I didn't answer the question. Right. So V0, what is V0? And V0 or V out, maybe V out equals VC minus VB. So let's go back to green, and V out equals VC minus VB, which is 2.133 plus 3.36, and I'm just going to go back to MATLAB and get it to do it for me. Right, so it's going to be ANDS 1 comma, so 2.33, 1 comma 2 comma 3, 2 comma 3 minus ANDS 1 comma 3. Right, VC minus VB, so it's 5.493 volts. Okay, thank you for reminding me that I need to answer the question. Okay, very good. Any other questions? Okay, so let's finish question 8 and then we'll have a break. So Giovanni, John, Mike, and Stephen. Any one of you want to lead me through solving this version?
Give it a try.
Okay, go ahead, Giovanni.
So we do have two freebies. So the voltage at node A is negative 15 volts. The voltage at node D is positive 10 volts.
Okay, sorry, Stephen. Yeah, VD. Okay, very good.
So that's how I went with. So KCL at node B equals IR1
Right, so that means you're going that way, right?
yeah minus IR2
Minus or plus?
minus.
Minus IR2, so you're
I
having...
did the opposite, yeah.
Okay, going that way?
IR2
Yep.
plus IR3 or 0.
Okay, so that's going that way. Very good.
And also for the KCL at node C, at negative IS
Mm-hmm.
minus I3 IR3
Yep.
minus IR4 equals 0. Then the KCL at node D, I did IR4 minus IR5 equals 0.
Now, I'll have to stop you there because, right, so I apologise for my dog going ballistic in the background. It's probably just another dog walking past. So there's there is also going to be a current flowing here, right? So for node D, this isn't quite the right equation for node D. Okay, because there's there is, even though it's a voltage source, there is current flowing from it or to it, depending on which way you look at it. So in order to get KCL at D, you need to include it. Unfortunately, because it's a voltage source, we don't know what that current is. On the plus side, we already know the voltage at D anyway, so these two equations here are probably enough for us to solve the system. Okay?
Can you explain the current flowing through R2 too?
The current flowing through R2. This one here?
Yeah. I was a little confused by that.
Okay, so which direction the current flows through a device is, or at least the way we assign the polarities is completely up to us. We could have done it. We could have done all of these exactly the other way around, right? And we would get the same answer, except the purple current values would be the negative of the green current values. And some people prefer, right, particularly for IR2, some people prefer to think about the current flowing from VB, from the node B down to the reference node, because that just makes us the current VB on 3900, right? Whereas if I did it with the, in fact, let me just do that in green, right? So the green version of IR2 is going to be just very simply VB. The implied piece is -0 because that's the other side, but all we need to do is divide VB by R2. The way I tend to do it is maybe a little bit more confusing, and the way I tend to do it by having the current flow into the node, it's the IR2 is then 0, which is where it's flowing from, the reference node, minus VB on R2, right? And as I said, the first way of doing it, the green way of doing it, gets us VB on R2, and the purple way of doing it gets us minus VB on R2. They're the same values numerically, but they're opposite sign. Does that answer the question?
I mean, I was more or less asking why weren't all of the currents all going into B, but I think I figured it out.
It's completely arbitrary, right? It's completely up to you to choose which direction, and I think it was Stephen chose this way of doing it, right? The directions as I said, my personal preference, and that's all it is. It's nothing, it's not a rule or a law. My personal preference is for one of the nodes on the circuit to have all of the currents flowing in. So that's why on the previous question 7, right? This is the way I would have done it. But this approach is exactly as correct. It's just a different way of labeling each of the currents. okay, which way the current is actually flowing will be told by the sign of the number that you get at the end. Right? If IR1 is negative, then the current's flowing the other way. If IR2 is positive, then that is the right direction that the current's flowing. Okay, so do we want to continue and try and get an answer with this one? Stephen, did you want to continue or?
After this.
Sorry?
I just got stuck after.
Oh, you got stuck. Okay, that's all right. So, so let's have a look at IR1. IR1 in the green direction is VA minus VB on 2700, and then minus IR2. IR2 is just VB on 3900, and IR3 going that way is VC minus VB on 3900 as well, and that equals 0. And then this one, that's minus 200 by 10 to the minus 6 because it's microamps. Minus IR3, so that's minus VC minus VB on the 3900, and then minus IR4, that's minus VC minus VD on 5600, and that equals 0. Okay, so let's use what we know. We know VA is 15 volts. So where did we have a VA? We had a VA there, so let's just make sure that we know that that's minus 15 volts, right? And we also knew that VD, which we've used here, is plus 10 volts. Okay, so now we've only got equations in unknowns VB and VC, so we can write that down. So the VB is minus 1 on 2700, minus 1 on 3900, minus 1 on 3900, and the VC is just 1 on 3900, and then the A, the constant term, is minus 15 on 2700 on this side, which makes it plus 15 on 2700 on the other side. And then rewriting this equation, we just get a plus 1 on 3900 for VB, minus minus, and then we get a minus 1 on 3900, and another VC is minus 1 on 5600, and then VD, it's minus minus, minus again for bringing it over that side, so it's minus 10 on 5600. Oops, and we have another constant, so plus 200 by 10 to the minus 6. Okay, so let's see what MATLAB makes of that. So that's Q8. Q8 equals minus 1 on 2700, minus 1 on 3900, minus 1 on 3900, 1 on 3900, 3900, not 2900. 15 on 2700. 1 on, not minus, just 1 on 3900. And then minus 1 on 3900. Minus 1 on 5600. And then it's minus 10 on 5600 plus 200 by 10 to the minus 6. Okay, so there's our RF equation. If we plug that into RF, I don't know what that's coming up for, but anyway. Some reason my phone decided to get involved in the so RFQ8. So there we've got a value for, just make room over on the other screen. We've got a value for VB of minus 6.312 volts and VC of minus 0.0754. Okay, so VB is minus 6.312, VC is minus 0.0754. Might need another significant figure. We still got to figure out what V out is, right? But at that, again, that's sort of looking okay. We've got minus 15 here, minus 6, a little bit negative, and then plus 10 volts there. And then let's look what V out is. V out is equal to VC minus VB, right? So V out equals VC, which is minus 0.0756, minus VB, which is plus 6.312, and let's see what MATLAB tells us that is. There's MATLAB gone, there's MATLAB, it's over there. Right, so that's going to be 5.4, not 5.6. Okay, so that's ANS 2, 3 minus ANS 1, 3. So 6.237 to 4 significant figures. Okay. Is everybody okay with that? Any questions?
I do have a question.
Okay.
So for R5, what about that one? You're just ignoring it.
Okay, so R5 is the information about R5, right, is already all there, right? Because we know that VD equals 10 volts, that means we know that IR5 is equal to V on R, which is equal to 10 on 2700, and that'll be amps. Okay, so we already know what the voltage across R5 is. We know what the resistance of R5 is, so we can solve IR5 directly. Okay, the issue with node D and applying KCL to node D is we don't know what the voltage source's current is, and we can't know it until we've finished the analysis, right? It's like the issue with current sources in mesh analysis. Current sources produce current, so we don't know what the voltage drop across a current source is until we've done the analysis. Does that answer the question, Steve?
Yeah, it does. Thanks.
Okay. Okay, so let's leave it there for now. I'll take. I'm a little later than my normal break time, but I wanted to get that tutorial done. So let's take a 10-minute break, and when we get back, what are we going to talk about? I've forgotten. We are going to talk about superposition, a new thing. Okay,
Can I ask a question about the homework?
Yeah.
For the last question in problem 6, I'm having trouble with making out the equations for the OP. I think it was called OP something.
Okay. I was going to go through homework 5 after superposition. Can you wait until then, or do you want me to go through it now? Have a look at it.
Yeah, I could wait.
Okay. So, which? Let me just write down which question. Which question did you want to look at?
Yeah, just give me a sec. Let me get back to the homework. It was question 6. It was the second part, I believe.
Okay. We'll make sure that we look at that when we go through the homework. Okay.
Thank you.
You're welcome. Okay, I'll reset that and go for a 10-minute break. See you on the other side.
Cabeza, carajo. Papote dice que se va a mechar con la mamá de su nena. Ayer fuimos a comprar hamburguesas. ¿Y sabe qué pasó? Rebotó su tarjeta. Y cuando se va a ver su tarjeta, porque tiene tarjeta separada, ¿no? Pero tiene una de Banco Americano.
Leonardo, I think you're unmuted, just so you know.
Sorry about that. I just needed to send an email. And I hadn't quite finished it when the timer went off. Okay, so let's go back to here. Okay, so we've done the tutorial 2 nodal analysis piece, and a little later on we'll have a look at the nodal analysis homework. I've had one question about question 6 there, but I'll walk through at least the first parts of most of the questions in nodal analysis in WebWork. But before we do that, I want to talk about a new topic. It's another algorithm. It's a little different from nodal analysis and mesh analysis in that it's sort of a meta-algorithm. And by meta-algorithm, I mean it doesn't actually solve the problem. It makes the problem easier to solve using either mesh analysis or nodal analysis. Okay, so let's have a quick look at that. And there's not that much to it, but it's something that is an important thing to cover, right? So this is superposition. Wherever we got to, there we are. So right, superposition. And here's the algorithm. You select each independent supply, whether it's a voltage supply or a current supply, doesn't matter, but they have to be independent. So they've got to be one of that, an independent voltage source, or that, also an independent voltage source, or that, an independent current source. It can't be a dependent source, which is a diamond, right? So you can't use, let's go with red, you can't use one of those, and you can't use one of those, right? You can only use one of these three. Okay, so that's what independent is saying. And what you do is you replace all the other independent sources with their ideal sources. And we haven't talked about what an ideal source is, right? But an ideal source is pretty simple. An ideal source sets the value to 0. Right? So if it's a voltage source, it sets the voltage on those sources to 0. If it's a current source, it sets the current on those sources to 0. So if I have a voltage source, right, and I make V, the voltage, go to 0, what does that look like? What does that replace the voltage source with? Let's play bingo. Mike Fedora, any thoughts on what if the voltage source has 0 volts that it's supplying, what can I replace that voltage source with?
I'm not 100% sure, but I feel like it's acting more like a resistor at that point.
Very close. What value of resistor do you think it's going to be?
I'm not sure.
That's okay. Okay, let me see if somebody else can... thank you for answering. Hunter, I think I've called on you before, but any thoughts on what we can replace this zero voltage source with? Mike was pretty close to the answer, but I need to know what the resistance would be.
I just realized my headset was muted. Sorry. I would think it'd be something like a constant current supply, but I really don't know other than that.
Okay. Constant current supply. Let's bingo somebody else. Dylan? I think I've talked to Dylan already today, right, too. So, Dylan, any thoughts?
Could we just model it as a resistor with zero resistance? Something like that? Just kind of make it a component?
Yeah, exactly. But it's even simpler than that. A resistor with zero resistance is a wire, right? So, whereas before I had a node on this side and a node on this side, now if the voltage between here and here is zero, I've just got one node, right? It's just a wire. Okay? So that's the voltage source ideal. Now for a current source, I've got the same question, right? So I have a current source, and now I make my current value go to zero. And let me bingo somebody else and see what I can replace my current source with. So Jonathan O, any thoughts on what I can replace my current source with?
I'm not really sure.
Okay. Let's try... well, I know the answer. I'm not going to give you the answer. Have to filter out the... Stephen, any thoughts? What I can replace the current source with? If the current goes to zero?
Open source.
Yeah, that's right. So if there's no current flowing, right? It's just an open circuit. There's a gap. I remove the source completely, right? So here I replace the voltage source with its ideal, which is a wire, and with a current source, when I replace it with its ideal, it's an open circuit, right? A gap. Okay, and then once you do that, obviously there's only one independent source in the circuit, so then you can solve that relatively simply. And then you repeat that exercise for each independent source. And then the tricky bit is once you've solved whatever circuit value you're interested in for all of those different circuits, you just sum the answers from each individual circuit, and that's the answer for the full circuit, right? The whole idea of superposition comes from linear systems, and it says that any independent source affects the circuit the same regardless of the effect of any other independent source. So I can just forget about all the other independent sources by using this ideal source idea, right? A short circuit for a voltage source. I should have written that down, right? A wire which is also a short circuit. Or an open circuit if it's a gap, if it's a current source. Right? Because they're independent sources, they don't care what anybody else is doing. They just have their effect, and that's the effect they have. You have to sum up the effects of multiple independent sources, and that's what superposition is telling you. Okay, another way to think about superposition is if you have a y1 equals f of x1 and y2 is f of x2, then the function f obeys superposition if y3 equals f of x1 plus x2 equals f of x1 plus f of x2. Right? You can think if f were non-linear, like if f were the square function, right, or the square root function, then those two lines there are not going to be equal. But if they are equal, then that means that the system obeys superposition. The system is linear. Okay. So here's an example of superposition. And the question, it doesn't actually have the question up there, but the question is asking, what is I out? Right? And you could do this question several different ways. When I ask you to solve a circuit using superposition, I want you to solve it using superposition, because I need you to show me that you understand superposition and how to apply it to a circuit. So the first step is to remove the source and replace it with its ideal. Remember, the VS1 is a voltage source, so we replace it with its ideal, and it's just a wire. So that's easy. And we can get, from that, we can get a value for I out, and it's the first I out value. Right? And let's just see if we can figure out what that is. Right, so let's see, VA, in this case, let's call it VA1 because it's the first version, is just going to be 5 divided by 10 plus 5 times 60. Right, so that's 1/3 of 60, which is 20 volts. Right, so that means that I out 1 is 20 volts on 10 ohms, which is 2 amps. Okay, all I'm doing to get this is I'm noticing that R1 and R2 are in parallel. So their equivalent resistance is 5 ohms, right? And they're connected between A and the reference. So effectively all I've got is a voltage divider with 10 ohms at the top and 5 ohms below it. So I can figure out what VA is just using the voltage divider equation. And that gives me 2 amps. So that's the first one. And then the second one, I get almost exactly the same circuit, but this time I replace VS2 with its ideal, which is a short circuit. And then I can do the same thing. And now VA2 is again, now R3 and R2 are in parallel this time, but they're both the same 10 ohm value. So those in parallel are 5 ohms. But now VS2 is 30 volts. So it's 1/3 of 30 volts, which is 10 volts. Right? So I know VA2, so I out 2 is equal to 10 volts on 10 ohms, which is 1 amp. Okay, so now I've got IO1, I have IO2. So then I can just say that I out equals 2 plus 1, which is equal to 3 amps. And in this particular example, I don't need to invoke mesh analysis or nodal analysis in order to solve the simpler circuit. I can just use the voltage divider equation to solve the simpler circuit. So let's have a look at how that might work with a current source in the loop, if you like. So similar circuit, except now our IS, and I don't know why I did it this way, it says IS is minus 3 amps, which means IS is flowing the opposite, the direction of the arrow. Anyway, so we first of all remove the voltage source, right? And now what we have effectively is we have, well, it's going in the other direction, so we have minus 3 amps right. I've just redrawn this equation, so this is R3 and then this is, I don't know, R2 and R1. Right, so effectively what I have here is a current divider. Right, I have IS flowing in here. And so because R1 and R2 are the same values, the current divider is going to divide equally between them. So the current flowing this way or this way is going to be equal to IS on 2. And that's going to be equal to minus 3 on 2. But I out is the negative, I out 1 is equal to the negative of IS on 2. So I out 1 is 2/3. Right? Lots of confusing changes of sign. So then I can remove the current source, and removing the current source means that there's an open circuit where the current...
Professor?
Yeah, what's up?
Sorry, would you mind going back and restating the I over 2 equation and how you got that, the IS over 2?
Okay, so if I have a... In fact, let's just draw it this way. If I have a circuit like this, right, where I have RA and RB, and I have I total, then the current through RA is equal to the resistance in the other branch divided by the total resistance in the two branches, that should be B, times I total. Right? That's the current divider equation. Just like the voltage divider equation, except that instead of the actual component, you look at the other branch in order to get the numerator. So what I did over here is I have IS flowing through R2 and R1. So I'm after what the current in R2 is. So I just said, well, the current in R2, right, and I'm saying that it's that direction, which is the same as that direction, IR2 is equal to the resistance in the other branch, which was 10 ohms, divided by the sum of the resistances in both branches, which is 10 plus 10, times IS. Right, so my IR2 going in the opposite direction of IR1 is IS on 2. Does that answer the question?
Yes, I got it now, thank you.
Okay, you're welcome. Okay, so if we remove the current source this time, we've got an open circuit. If there's an open circuit, there's nowhere for the current on the right hand side of R3 to flow. That means there's no current coming out of there. So we can simplify the circuit even more, and we just get this. And obviously now we have IO2 equals V on R, Vs on R total. And Vs is 30 volts. And R total, the R1 and R2 are just in series. So they're 20 ohms. So IO2 is just 1.5 amps. Right, so then the overall current, and you might want to think about that as the total, is equal to 2/3 plus, what was it, 1.5. Did I say 2/3? Is that right? Why did I do 2/3?
I think it's 3/2.
You're right. I made a mistake. I wrote it down completely the wrong way around, right? So 3 on 2, and I should have given it a unit as well. 3 on 2 amps. Okay, so then our total current is, let's get that right. Let's try that again. Sorry about that. Right, is 3 over 2 plus 1.5, which is the same thing, which is 3 amps.
Could you scroll to the slide before that?
Okay, so this is the equivalent circuit once we've removed the current source. So we just get...
okay, thanks.
Yep, you're welcome. Okay, and that's a really simple introduction to superposition. I'm not going to be able to get on to the tutorial yet, today probably, but there are tutorial problems available. I haven't uploaded it into Blackboard. Let me do that now so that they're available. Right, so let's upload a file, and this is tutorial 03, and this is superposition, Thevenin and Norton. And I'll make that available in Blackboard as well as in OneNote. You probably don't want to look at that. Okay, so the superposition questions on the tutorial are a little bit more complicated, and there's only 2 of them, so I might see about releasing the second midterm earlier rather than later, just to show you what previous second midterms have looked like. Maybe, if I can figure out where the course got to. Here it is. I think I need to go there, because I need to go to an older version. Let's go with the summer course. Right, and this is, I'm going to update this for, oh, there it got to. Right, so the it's going to be very similar to the format of the midterm that's currently open. There's 2 topics, mesh analysis and nodal analysis, and I'm going to give you a couple of questions in each, and just like the current midterm, I'm going to ask you to answer one, or walk me through how you would solve each question. There are no numbers on either question. Once you've given me your explanation about how to solve each circuit, I'll then give you some numbers, and you can then go and solve the circuit numerically offline. And again, in this case, the weightings will be 1/3 on the mesh analysis oral question, 1/3 on the nodal analysis oral question, and then 1/3 on the written submission answers to both mesh and nodal analysis. I didn't want to do that. Let's get out of Visual Studio, shall we? Okay, let's see what's next. So I've talked about superposition. I think the main thing we need to do now is to get you to apply mesh analysis and nodal analysis a bit more. And part of doing that will be applying also superposition. And we'll do that superposition, those two superposition tutorial questions next week. I might see if I can generate another couple of questions, but I thought I might as well release the tutorial now so you can have a look at it. But I might add so that we can. I think it's useful to have the four smaller groups working on individual problems. Okay, so lab 4, I believe, is due today. Does anybody have any questions about lab 4?
What exact numbers do you want for the nodal analysis on that lab? Like, are there any specifics, or just like the voltage for them?
Sorry, nodal analysis.
Never mind, I think I'm doing lab 5 by accident. My bad.
Yeah, so lab 5, I will go through lab 5 shortly, but lab 4, I believe, is due this evening. Let's just check. Yeah, so lab 4 is due this evening, so I thought I'd ask questions about... Everybody okay with...
Yeah, no, I got it mixed up. That was my fault.
No, it's okay. I will get on... I did want to introduce lab 5 as well, but let me do that before you ask your question, okay? So there we go. It should be pretty straightforward. Just make sure that you... so just some general feedback on the labs. Make sure that you label voltage polarities, you label current directions, you use the same units across all appropriate measurements. For example, some people have been chopping and changing between amps and milliamps. I'm okay with either, provided I can see enough significant figures. But if you use milliamps in some places and amps in other places, that tends to get confusing. So try and use the same unit for current everywhere, and the same unit for voltage everywhere, and the same unit for resistance everywhere. Right? Resistance, it's usually either ohms or kilo ohms. I don't care which one, but choose one and stick to it. Same with voltage. Sometimes it's millivolts, sometimes it's kilovolts. Sometimes it's just volts. Choose one and stick to it. Chopping and changing tends to lead to confusion. Of me more than anything else, and if I'm confused, I'm not going to give you the right grade. Okay, so let's have a look at lab 5. So lab 5 is about mesh analysis and nodal analysis. Right? And we've gone through both mesh analysis and nodal analysis enough. What are the objectives? Study mesh analysis and its usage in multi-source DC circuits. Study nodal analysis and its usage in multi-source DC circuits. Application of mesh and nodal analysis to finding circuit currents and voltages will be investigated. So basically, you've got to put together that circuit and write down what voltages and resistance values you use. Oh, actually, there's the the voltages, and that should be V2, I think, rather than V5. Yeah, V2. I'll have to fix that. And measure all of the currents and voltages across each resistor and the voltages at each node in the circuit, and then analyze the circuit using mesh analysis, and then analyze the circuit using nodal analysis. And believe it or not, the answers you get should be the same. If they're not the same, there's a problem. Okay, so that should be pretty straightforward. Let's just take a look at the circuit, and this is lab 5. So let's just make a new page, and we'll insert that picture, and let's do some drawing for mesh analysis and then some drawing for nodal analysis. Okay, so for mesh analysis, right, the first thing is to define your mesh currents. So there's I1, and I'm just going to go that way with I2, and try and remember to write down the polarities. Your voltage sources don't change. Your other components, your passive components, should follow the passive sign convention. So that's a plus there and a minus there and a plus there and a minus there. Okay, and then you should be able to see that the mesh for I1 has minus V1 plus VR2 plus, sorry, VR1, that should be, plus VR1 plus VR2 plus V2 equals 0. And then the mesh for I2 has a minus V2, a plus VR2, a plus VR3 equals 0. And that should get you started. And remember, then you've got to replace the resistor voltages with Ohm's law. So R2 in the red mesh is going to be I2 minus I1 times R2, and VR3 is just going to be I2 times R3, and in the blue mesh VR1 is just I1 R1, VR2 is I1 minus I2 R2, right? And then V1 is whatever the sheet said it was, and V2 is whatever the sheet said it was. Now, this one's a little trickier, right? For nodal analysis, now we've got to figure out where the nodes are. So there's a node here, there's a node here, and there's a node here. There's also a node down here, but that's the reference node. So we don't actually have to explicitly solve that one. So let's just, I would just call this node A, maybe that's node B, and maybe that's node C. Could have called C, swapped C and B in their names. Okay, so there's the start for that. The nice thing about this one is that we get VA equals V1 directly, and we get VB equals V2 directly. And then the only thing we need to figure out is what's happening at C. And again, my personal preference for defining current directions is to have one node where there's define one node where there's all of the currents flowing in. So then I get my, oops, let's go with that. I get my IR1 plus IR2 plus IR3 equals 0. So IR1 is VA minus VC on R1. IR2 is VB minus VC on R2. And IR3 is 0 minus VC on R3. And that equals 0. And then the aim is that you can set the circuit up into LT Spice. And I don't think I need to demonstrate that. You should be able to do that in LT Spice now. And measure all the voltages and the currents. And the things you've got to measure are, what do you have to measure? You've got to measure VA, VB, VC, VR1, VR2, VR3, right? VR3 and VC are the same, right? Because R3 is just between 0 and VC. R2, depending on how you define it, but if I have my polarity like that, which maybe I don't, maybe that's not the right way to do it. Maybe because I've got my current flowing that way, I need to have it that way, right? Then my VR2 is VB minus VC. Because of my current flow in R1, to make it satisfy the passive sign convention, I need to have VA minus VC. Any questions about Lab 5?
For the resistors, do we get to pick, like, for R1, could we pick like 100, R2 200, R2 300?
Mm-hmm. It's completely up to you what values of resistors to pick. I usually go with something simple like that, 100, 200, 300. I prefer them being different. Otherwise you tend to get if they're not different, you can make numerical errors and still get the right answer. Whereas I'd rather you pick up on your numerical errors and figure out why you're making your mistakes to hopefully correct them so you can self-correct. Okay? Okay, so I've done lab questions, and I think we should look at homework 5 now. And I did have one specific question about question 6, so I should make sure I answer that. And let's make that a bit bigger so we can see it on the video. So the so mesh analysis is going to close. Ooh, why is nodal analysis closing there? I thought I'd change that to close next week. That's no good. Let's edit that and make sure that it's open until the 20th. I was sure I'd changed that, but apparently I didn't. So let's edit that, and we'll make it due on the 20th. This is nodal analysis. Okay, so now it is due on the 20th. Apologies for that. I'm going to have to move the Thevenin and Norton one as well. Apparently I didn't move the WebWork ones off, but we can leave Thevenin and Norton. Okay, so nodal analysis. Let's quickly, we did have that one question, so let's just look at question 6 first. I might go backwards through it. Question 6, 5, 4, 3, 2, 1. Ooh. I knew there. Okay, I had forgotten that question 6 has an op-amp in it. Right, and I haven't talked at all about op-amps, and I hadn't been intending to talk about op-amps. So I should talk about op-amps. So let me talk about op-amps. So let's add another page, and this is so op-amps, particularly ideal op-amps. Ideal op-amps are drawn like this. Right, an op-amp, that I'm using the shorthand name, is what's called, in full name, operational amplifier. And it's even better in this course, we're only dealing with ideal operational amplifiers. And ideal operational amplifiers have a few ideal properties, funnily enough. And the key thing about an amplifier is its gain. How much does it amplify the input by? In this particular case, it's actually what's called a differential amplifier because there's a minus sign on one of the inputs, right? And in general, an operational amplifier amplifies the difference between, if it's a differential operational amplifier, it amplifies the difference between the inputs. In this case, V2 minus V1 times K. And K is called the gain. Okay, that should be reasonably straightforward. Now the trick, and the thing that sounds a little bit odd when you think about it, the trick with an ideal operational amplifier is that the gain is infinite. Okay, so if there's any difference at all between V2 and V1, the output is either positive infinity or negative infinity. Obviously, on a real device, you can't do that. It'd be wonderful if you could, but you can't. But even on a real device, the gain is usually pretty high. It's usually of the order of 100,000. Right? So multiplying 1 millivolt would get you 100 volts out. So K equals infinity is not too bad an assumption. But there's a few things that flow from that K equals infinity. One of them is this. Oftentimes when you have a circuit with an operational amplifier, one of the inputs is grounded. Okay? Because of that ideal, the difference in voltage between the inverting input, that's what this one's called, the inverting input, and the non-inverting input, the difference in voltage between the two of them has to be zero. So what that means is that the voltage here is zero as well. And that is completely because our, sorry, I had to go blue. That is completely because of our ideal assumption that there's infinite gain. And this property of an ideal operational amplifier is called a virtual earth. Okay? A virtual earth. Okay. There's a couple of other properties of ideal operational amplifiers. One of them is that the input current on each of the inputs is zero. So you get zero current flowing in. So when you need to apply Kirchhoff's current law, there's no current flow through that particular branch of the circuit. Again, so that's another thing. So one of the things is infinite gain. Second thing is no input current. I suppose the second thing should have been the virtual earth. So let's just add. No, why is it not? Oh, it's because I'm trying to do. It stopped. Let me just take a screenshot of that, and I'm going to have to kill. I think it might be because I'm going into full screen. Maybe if I stop going into full screen, it'll not do that. Yeah, I lost all of my notes. Let's just insert that screenshot. Okay, so the third thing I was going to add was the virtual earth. Okay, so now let's go back and have a look at what that all means for this question, right? So let's copy the image and see what it's saying. So this one, it's a little different, right? Here's our reference node. So our v equals 0 node is all down here, right? So VB equals minus VS. But remember, the gain of this thing is infinite. Because of that infinity, we need we need the difference in the voltage between the non-inverting input, this one, and the inverting input to be 0 volts. So that means the voltage here is also minus Vs. Okay, so let's look at nodal analysis. What do we need to do with nodal analysis? Well, we have a node A, we have a node B, and I think it's just a node O. Okay, so the things we've got to figure out are VA, VB, and VO. So what's the homework asking? The homework is asking how many KVL equations are needed, how many KCL equations are needed? Well, so KVL, there's at least one KVL for node B, right? And I suspect you could think about node A as either a KCL equation or a KVL equation. And then node O is a KCL, probably. Although maybe that's a KVL as well, because the problem with applying KCL at node O is that we're not sure what the current output of an op amp is. Right? It could be lots. So let's have a look at what WebWork thinks it is. So I suspect the numbers are 2 and 1. Okay? And remember, the reason I think there's 2 and 1 is because, well, there's definitely 1 here, and I suspect there's 1 here as well. There's going to be a KCL equation for node A because you've got IS flowing into it and you've got IR1 flowing into it. Okay, so there it says there, that's what it thinks, right? KCL at node A. So what's happening at node A? And we can use VA, VB, or V out as our VO as our variable. So KCL at A, let's just go do some drawing. So KCL at A. Right, we have IS and we have IR1. So the KCL at A is going to be IS. There's also this one here, but remember, because this is an ideal operational amplifier, that's 0. So we can ignore it. So IS plus IR1 equals 0. And that's IS plus IR1 is V out minus VA on R1. And that equals 0. So V out minus VA on R1. So let's try and put that into the equation. So IS is 25 microamps. Okay. And then what did I have? Plus V out minus VA on R1. So plus V out minus VA on R1. R1 is 18,000. Let's just check our answers. We've got to say equals 0, right? It needs to be an equation. Your equation isn't a linear one. Oh, it probably doesn't like that. I'm wondering if I need to do something more like that. Oops, that. Your formula isn't a linear one. That's interesting. Let's just write it out without Okay, that's 25 microamps in terms of amps. My formula isn't a linear one. So I'm going to cheat and check my answers. Okay. That is not making any sense to me. I think this is just this number. I'm not sure where it's getting. Oh, does seem to think it's got to have VA and V out in there, but this, I don't know what the E is. If the E here is yes. So let's do this. Let's not do question 6. This isn't doing the right thing, and I believe Professor Broderick updated WebWork to the more recent version, and it's got some problem with the way this particular question is worded. So let's ignore question. Yeah, what's up?
I got 0.55 minus VA plus V0 for the case here at A.
Sorry, what did you get? Could you say that again?
0.55 minus VA plus V0 equals 0.
Like that. Could you explain how you got that one?
So for sorry, so we know that IS is entering, then that means that since VB and VA have the same voltages, then that means for the VA will equal to VB, which equal to the voltage at VS. Then what's the voltage?
It's minus 4 volt. Well, VS is 4 volts.
We also know that the current entering into the two what's that? Is it the op amps is 0 for both. That means the VS is entering. That means there's a current leaving in IR1. So when we do the the voltage thing, the node voltages, we should get IS equals to VA minus V0 divided by R1 equal to 0, and then from there.
Okay. I'm just going to, so this is what you got for KCL. Let's just check to see what, yeah, see it's giving the same thing that it thinks is the right answer. And I don't think that's, I can't explain what it's meaning because I'm not sure what the E is between here and here. Normally when the E shows up, it means that there's a numerical instability problem in the answer. So yeah, that's what I would believe. Okay, I apologise for that. I think it's a like I said, it's an update. Let me just see, while we're here, let me just walk through the way I would solve it. All right, and let me just grab the numbers from my. Right, so there's the numbers, and if it were working properly, let's insert that screenshot there. So I know what the values are. Okay, so in that case, that's the KCL at A. I think it should also be a KVL at V out and a KVL at B. Let's just see if I'm just going to see, because KVL at B should be direct, right? It should say just VB equals minus 4 volts. Let's just check that. Yeah, it thinks that's right. And then the oh, I see. The KVL that it's talking about is just the difference between, is just the virtual earth, right? VA minus VB equals 0. And I'm just going to put my suggested answer in back in here. What was it? It was that IS plus V out minus VA on R1. IS, which is plus V out minus VA on R1 equals 0. I'm pretty sure my equation's a linear one, so I'm not sure why it's complaining about it being a linear one. I'm going to see if Professor Broderick has a suggestion. For some reason my mouse cursor keeps disappearing. So then the answers will be that VA is minus 4 volts, VB is minus 4 volts, and V out we're going to need to solve this, right? So it's going to be, let's just go back here and see, where's my pen gone? There it is. So it's going to be so V out minus VA on R1 equals minus IS, V out minus VA equals minus R1 IS, so V out equals minus R1 IS plus VA. And it's
sorry to interrupt, Professor.
Yeah, what's up?
I realized I gave you the wrong answer for the first one. When I redid it again, I got 0.45 plus VA minus V0 equals 0.
Okay. So then my V out, sorry, is going to be minus R1 IS plus VA, right? And that's going to be minus 18,000 times 25 times 10 to the minus 6, and then plus VA. VA will be minus 4. So let's see what that comes out to be. Let's just bring up MATLAB. Right, so V out equals minus 18,000 times 25 by 10 to the minus 6 minus 4. So minus 4.45. Let's see if that's what. And then again, that's volts. Let's see if that's what. Yeah, it gets it right. And then the output current, I haven't defined the output current yet, but the output current is just going to be V out divided by R2, right? So minus 4.545 divided by 18,000. So let's see what that is in MATLAB. Right, so that's minus 2.4 minus 0.2472 milliamps, although it probably wants so what's that? It's going to be minus 2.47 by 10 to the minus 4. So if it were 10 to the minus 3, it'd be there. 10 to the minus 4, 2472. And then the answer is in amps. And let's see if that. Yep. So I can solve the question. I just can't solve the problem with web work. Okay, so yes, there was a fundamental problem with web work rather than, oh, plus I hadn't talked about op amps. I apologize for that. I'd forgotten that there was some op amp questions here. So I hope that's given you some feeling for how to do the op amp question. I'll tell you what, I'll leave question 6 here. If anybody makes an attempt at question 6, that'll be bonus marks for question 6. So you can do questions. Let's make sure we can do questions 1 to 5, but we'll leave question 6 as a bonus. Any other questions about question 6? So question 5, again, nodal analysis, and in this case the nodes are already defined. There's a little bit of complexity because there's a dependent source in V2, right? But other than that, I think we're all good. So I think that one's okay. The types of equations. There's 2 KVL equations, right? The KVL equations are for node A, because we've got a voltage source connected between the reference and node A. And for node C, we've got a voltage source. Even though it's a dependent source, it's still connected between the reference and the node. So we can just write that VC equals V2, or VC equals 2V out. So let's have a look at question 4. Okay, so question 4 for nodal analysis is a supernode question. It's a supernode question because VS is a voltage source that is not connected to the reference node. It's connected between two non-reference nodes. So we need to make sure that instead of having a KCl equation at node A and a KCl equation at node B, we combine nodes A and B into a supernode, and we write a KVL equation and a KCl equation for the supernode. The KVL equation is going to be VA minus VB equals VS. And then the KCl equation is going to be I1 plus IR2 if IR2 is going up into the node, plus IR1 if IR1 is going up into the node, plus I2 equals 0. Because we just combine the nodes A and B into a single supernode. So we should get that there's only two equations, so there's going to be one KVL. There's only two unknowns because there's only two nodes. So we should get 1 and 1 for that one. Okay, that's question 4. Question 3. Again, we've got a supernode, V2 is connected between nodes B and C. And in this case we have 4 non-reference nodes, A, B, C and D. So I suspect that means we have one KVL equation and 3 KCl equations. Let's just check. No, completely wrong. Oh no, we've got a KVL equation here too, right? Because we've got two voltage sources. That probably means we have two KVL equations. In one case, in the V1 case, the KVL equation is just VA equals V1, direct, right? That's the freebie. And then the supernode gives us another KVL equation, and that KVL equation is VB minus VC equals V2. So that should be, now we've got two of each, right? Two Kirchhoff's current law equations and two Kirchhoff's voltage law equations. And then problem 2. And this one, again, we've got a supernode at B and C. Right, you can see V2 is not connected to the reference node. Only V1 is. And again, we probably have a 2 and 2 split. Ooh, no. Oh no, there's fewer nodes. It should be 2 and 1 this time. Right, there's only A, B and C. There's only 3 unknowns. There's only 3 nodes, so we only need 3 equations. And then finally, or initially, question 1. We have one voltage source, and so we can write down the voltage at A immediately. So that's our, I think it's going to be a single KVL equation for node A, and then node B and C we can write down KCL equations. So I suspect that's what's happening with KCL. Okay, so that is homework 5, and it should now be correct. The due date should be the same in both WebWork and in Blackboard. Let's just check that I got it right in Blackboard, just because I didn't get it right in WebWork. So, right, homework 5, nodal analysis, is due Saturday next week. So I think that's the same in both now. Okay, let's have a look at where we are. So I've gone through what I wanted to get through in today's class. I'm not going to talk about maximum power transfer. One thing I am going to do, I do think I have some separate notes about op amps. Let me just check to see that I do. I do. There we go. So let me, what I'm going to do is I'm going to add them here so that you've got access to them, and I might talk about them in more again next week. Nope, wrong one. It's that one I want. And it's decided to lose the checks, right? And there's a lot more in here than what I talked about. One thing if you're in any way interested in measuring stuff for robotics or for mechanical engineering, then one of the things that people usually want to measure is strain using strain gauges. And the problem with strain gauges is they don't give you much of an output. So oftentimes you need to put a gain, an amplifier, onto the strain gauge. And op amps are the usual way you would get a nice gain on measuring strain, for example. Other measurements as well. Okay. So that's available now. I'll just put it down the bottom here. So next week, and my tick's going there. Next week I will look at maximum power transfer. And I will look at the ideal op amps in a bit more detail, just so that you've got that information. I had forgotten that the nodal analysis question had an op amp in it. I should have remembered that. Does anybody have any questions about the lab due today, the lab due next week, or the homework assignment due next week? Okay, if not, it's a little early, but let's leave it there for today. I think I'm pretty much on schedule, so please use the time to get the homework done or get the lab done. And I will use the time to try and grade your homework once I've had some lunch, I think. Okay, let's leave it there. Thank you very much for your time today. And I will talk to you later.